Hello there, students, and welcome to our class notes, Introduction to Stoichiometry, class notes 9-9. It's a little sad to say that this is actually our last notes of the entire school year, our last notes of e-learning. There will be some help videos later, but they are not actual class notes. So for me, it's a little sad that these are our last class notes, but hopefully for you, it's a great feeling that knowing we have light at the end of the tunnel. We're taking a look now at a chart that we used all the way back. I believe it was in Unit 7, where we learned to convert volume to moles and moles to volume using the fact that 1 mole of any gas at STP, standard temperature and pressure, takes up 22.4 liters. We learned earlier this year that if you knew quantity count, formula units, ions, atoms, or molecules are the units for quantity count. And if you wanted to know moles, or if you knew moles, you knew the exact quantity contained in those moles. There we used Avogadro's number, where 1 mole of anything is 6.02 or 6.022 times 10 to the 23rd. One of the first calculations we used, and one of the most fundamental that we learned several units ago, was converting mass to moles and moles to mass. And we saw the importance of that calculation was the fact that chemical equations, the coefficients in chemical equations reflect moles, but in the actual lab setting, we use balances to measure mass. But if we knew how much mass we had, we knew how many moles we have. If we know how many moles we have, we know what its mass can be by simply adding up the molar mass from the periodic table of elements. This chart was a very important chart, and we see at the hub of this chart is moles. Moles are the unifying concept in chemistry. But for many of you, when you looked at this chart, you may have looked at it with a little bit of confusion. It might have thrown you off balance a little bit when you looked at it, because here we have moles in the center of the chart. Right in here, in the center of the chart, we have volumes to the north, quantity count to the west, mass to the south, but what do we have to the east? This chart is lopsided. What do we have going off this direction? Is there something else we can convert moles to? Thank goodness there is. Ladies and gentlemen, it's with great pleasure that we finish up our last set of notes, realizing that there's an uncharted territory to the east of moles. Moles can be converted to something else. And today we will talk about what else moles can be converted to. It may be the single greatest lesson of the entire year. It may be the most important aspect of chemistry. We spent a good chunk of our e-learning working with chemical equations, balancing chemical equations, learning the types of chemical equations. That was Unit 8. And we just didn't do Unit 8 because it was incredibly interesting. We did Unit 8 because chemical equations reflect mole-to-mole ratios. Those coefficients give us a relationship between every substance involved in that chemical equation. The mole-to-moles give proportions of one substance to another. And that is what the subject of stoichiometry is all about. Today we have our introduction to stoichiometry. Stoichiometry is looking at the proportions that are reflected in the chemical equation, because when we have a chemical equation, ladies and gentlemen, we can convert mole of one thing to mole of something else, and we learned to do that earlier this week. But that is the base, that is the starting point of a whole new type of calculations. Mole to moles is a very common equation. It's the component which allows us to discover many other things about substances and chemical equations. So when we have a chemical equation, we can convert mole of one thing to mole of something else in that equation. And when we do that, get ready for this, an entirely new chart comes about. Much the same as this chart, but we will have the uncharted territory revealed. I wish we had a drum roll. We don't. Pretend there's a drum roll in your head. What if we can go mole to mole? What else can we find? Here it comes. The stoichiometry conversion chart. What we learned to do earlier this week was to convert mole of one thing to mole of something else using the coefficients from the balanced chemical equation. So this is the side of the chart that we already worked on. The red side of the chart is the part of the chart that we've already been accustomed to back in Unit 7, where we could go moles to volume, volume to moles, moles to mass. Mass is now on this side for reasons you'll soon see, mass to moles. Or we can go moles to quantity count to moles. In our previous chart, we had quantity count over here, but we do want to move it to the bottom. The earlier conversions, we always dealt with one particular substance. But now that we have a chemical equation, if we know one thing about one substance in the equation, if we know the volume, the mass, the moles, or quantity count of one substance in the chemical equation, we can find out anything about any other substance in that chemical equation, provided we have the balanced chemical equation right here. When you have a balanced chemical equation, we can convert moles of one thing to moles of another. The thing we're converting to is the entire new side of this chart. So the green side of this chart is what we're finding out about something else in the equation. So this is our given side. They will give you something about one thing in a chemical equation, and they'll ask us to find out something about something else in the chemical equation. To do that, we do this blue bridge right here. This is the mole to mole thing. This is a mole to mole conversion. We just put the moles of what we're trying to find on top. The moles of the substance we're given will go on the bottom, and we have a whole new world unlocked for us. If you know any of these things and you use the mole to mole conversion, you can find any of these things. We'll be looking at some sample problems here. Now this chart may look a little different. On the previous chart, we had an arrow going up, an arrow going back. There were arrows going from moles back to everything else. This is the way the chart used to look. If you knew moles, you could go up and back, up and back, up and back. But when we're doing stoichiometry, we're not trying to go find something else about a particular substance. We want to use the chemical equation to discover something else about an entirely different substance. So for instance, they might give you the volume of a gas in an equation and ask you for the mass of something else in the equation. In order to do that, you would take the volume of that substance and you would convert it to moles. Then we would use the chemical equation to go mole to mole. Then we would go mole to mass. That would be 3 steps. First step, we would have mole over 22.4 liters. Second step, we would use the mole to mole ratios in the chemical equation. And then in our third step, we would go mass of the periodic table of the substance we're trying to find divided by moles. This is just the same stuff we've already learned to do. One of the most common one of the most common problems in all of chemistry is called a mass-to-mass stoichiometry, where they would give you the grams of something in a reaction and ask you the mass of something else involved in the reaction. For instance, they might say, how many grams of some product could you make from a certain number of grams of reactants? Well, how would we do it? They gave us the mass of the reactants. Our first step would be to put 1 mole of that substance divided by its molar mass from the periodic table. Then when you use the chemical equation, and we would put moles of what we're trying to find over moles of what we're given. That would get us right there, and then we would go to the mass by multiplying by the molar mass over 1 mole, or the mass over 1 mole of it. So that would be 1, 2, 3 steps. Many of these problems will be 3 steps. We could work with quantity count as well. They could give you, for instance, ask you how many molecules of water you could make from a certain volume of oxygen. A certain volume of oxygen. So they gave us a volume of oxygen and they want to know how many molecules of water you could make. How many steps would that problem be? 1, 2, 3. First, we would divide by 22.4 liters. 1 mole of any gas is 22.4 liters. So if they gave you the volume of that gas, you would multiply it by 1 mole over 22.4. Then when you use the balanced chemical equation, like we learned to do Monday, Tuesday, mole of what we're trying to find, water, over moles of what we're given, oxygen. We know from the chemical equation for water, it's 2 moles of hydrogen for every 1 mole of oxygen to make 2 moles of water. So we'd have 2 moles of water on top, 1 mole of oxygen would be on the bottom. And they want to know how many molecules we would get. So we would be going down this way. There are 6.022 times 10 to the 23rd molecules of water in 1 mole. Now, if you notice, this is our standard bearer for discovery to the new territory, a mole-to-mole conversion. But we notice that there are 2 shortcuts on this chart, quantity count to quantity count and volume to volume. This is a shortcut. So for instance, if they said you had 2 liters of hydrogen, how many liters of, or let's say 4 liters of hydrogen, how many liters of oxygen would you need to burn it to make water? 4 liters of hydrogen, how many liters of oxygen would you need? Well, we could go this route. 1 mole over 22.4 would get us to moles. Then we know that it's 1 mole of oxygen for every 2 moles of hydrogen gas. That would go right here. Then we would blast up this line, and it's 22.4 liters of oxygen for every 1 mole. But take a look. When you're going from this thing to this thing, we're going to divide by 22.4 liters on the first step, mole-to-mole ratio, and then we're going to multiply by 22.4 liters in our third and final conversion. 22.4 divided by 22.4 cancels. So the first conversion would be canceled by the third conversion. So really the only thing we needed to do was use the coefficients from the balanced chemical equation. So a volume to volume shortcut. Coefficient, there's 1 liter of oxygen for every 2 liters of hydrogen, 2H2 plus 1 O2. Those would be the only coefficients we would have left. It's 1 liter of oxygen needed for every 2 liters. So if we had 4 liters of hydrogen, we would multiply it by 1 liter of oxygen over 2 liters of hydrogen. You would only need 2 liters of oxygen. We will be doing example problems, so if you're like, I sure would like to be seeing example problems, we're going to be doing example problems. Right now, we're just talking about how this chart works out. The same conversion happens if they were trying to convert a quantity count to quantity count. There is a shortcut here as well. So if we're working with atoms, ions, molecules, or formula units, and they're asking for atoms, ions, units, or molecules or formula units, if they give you any of these 4, and they ask for how many of atoms, ions, molecules, or formula units of something else you would need, we could go here, over, and down. On our first step, we would be dividing by Avogadro's number. In our last conversion, we would be multiplying by Avogadro's number. Those 2 would cancel out, which means the only thing we really need to do is work with the coefficients. That's all you would need to do. And that's the shortcut right there. And we'll get a chance to look at that shortcut later. But in this particular video, we were just hoping for you to take a look at this new conversion chart, get an idea of what is on it and how it will work. And in our next video, we will take a look at some example problems so that you can see how it actually lays out. Thank you. It's our last set of notes for the school year. I hope you are enjoying these.